not a subgroup? Because it's not closed. Now, why is that? Well, take two elements. Let's say A and B. Belong to this. They belong to Q star, and let B equal minus A. Right? So choose anything. I know 4 and minus 4, whatever. So when you add these two, because the binary operation is add, so A plus B would then be A plus minus A, which gives you 0. But 0 does not belong to this set. Okay? So it's not closed. The result of a binary operation, so in a sense A binary operation with B gives you 0. And 0 is an element that does not belong to this set, so it's not closed. So this H cannot be, it's not a group, and therefore it cannot be a subgroup of G. Okay, so a few more examples. Let G, let's put it here. G now is the set of all complex numbers, so obviously an infinite set, right? The set of all complex numbers except the 0. Right? You throw out the 0. Now, why all this throwing out 0 every time? Because if you don't do it, things don't work. Things get messy and you can't do anything. And so it's just much more interesting to throw out the 0 and work with what's left. The reason for that is anything times 0 is 0. So so the presence of that 0 just ruins everything. Okay. So the parent group, if you like, the group G, big G, is the non-zero complex numbers. And the binary operation is times, just multiplying any two complex numbers. Okay. Now, here are some, in fact several, three different subgroups, not just subsets, but subgroups of big G. Right? So that's why I put it H here. So one of the, watch. So here's your complex plane. Right? So Z is x plus IY. Yeah, I assume you've done some undergraduate complex number theory. Okay. So this radius, the radius of this circle, let that be 1. Okay. So this set here, it's the set of all points in your Argand diagram. This is the Argand diagram, the complex plane, if you like, same thing. So it's the set of all points lying in the complex plane, such that the distance from the point, so let's say that's point xy, so it'd be the complex number z xy, this point here, and the distance here from the center, the origin, is 1. Okay, so this set here is all those complex numbers that lie on this unit circle. Okay, and you can prove that that's a group, so, right? infinite group. It's not too hard. You can do that as an exercise, bit of homework. Prove that this is a group. It satisfies the 4 properties of a group and the binary operation, which is just multiply. So you're just multiplying 2 complex numbers. Now this one is a smaller subgroup than this one. Okay? And in fact, interestingly, this one is a subgroup of this one. And this one is a subgroup of that. So you might like to prove this. If you have a subgroup of a group, and that group itself is a subgroup of a larger group, so you've got like 3 levels in a sense, the bigger one, the middle one, and the lower one. Question: how do you prove that the lower one, the smallest of the three, is a subgroup of the biggest? Try that for homework. Alright, so this is a subgroup of this, and it works out that this is also a subgroup of the big one. Now, this one, so, well, let's draw that. So this subgroup is in fact these 4 points, here, 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 and here. Okay? Now, there's an even smaller, so we're now a fourth. So, 1, 2, 3, 4 groups, consisting, this one just consists of these 2 points, okay? Plus minus 1. And that is also a group. So this is a subgroup of that one, this one's a subgroup of that one, and that one's a subgroup of that one. Now, I'm giving you a taste of group structure. You can actually decompose a group down, 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 down. And there's all kinds of theory about that. And but we won't do it in this text because it's sort of graduate level. But if you're interested in group theory, I will definitely be giving courses on higher level finite group theory that talks about the structure, the internal structure of a group, and you can decompose it, go down, 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 and you can have huge groups so that you can decompose a lot. There's like a whole chain of getting smaller and smaller groups. And can you do that in a unique way or not? I mean, can you decompose in different ways and blah, blah, blah. So I will definitely be giving higher level, graduate level, master's level, and in some cases I will even go up to PhD 2 level on some of this stuff. Very, very advanced stuff and difficult, but that's a while away. I have to get through all the master's courses. I have hundreds of them to do, so it'll take me ages. Okay. Right, here's another one. You have the group is just the set of integers, just Z here, or if you're British, Z. And the binary operation is just plus, that's a group. Okay, so this set, dot 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 dot, -4, -2, 0, 2, 4, dot dot dot, call that set H. It's actually a group with this binary operation of plus, okay? So, and H is obviously a subset of Z. Okay? Z is the set of all integers. And this, if you look at it, is the set of all even integers. So H in a sense you can rewrite as 2Z, okay, with the binary operation plus. So this H, this subset here, is a subgroup of Z. Okay, so that's very obvious. Right. Now, if you look at a table like this, it's fairly easy to see whether something is a subgroup or not. You just almost by visual inspection. Okay. But if your group is large, or infinite group, you need some method, some procedure, some well-tested way of doing things that allows you to prove that some subset that you think, you're suspicious, or you suspect that a particular subset of the group you're talking about is actually a group. Right? So you need some method, some step-by-step procedure to allow you to prove that your suspected subgroup is actually a subgroup. Now, how do you do that? So we want now a kind of test for that a subset is a subgroup. Okay? So we're looking for a test for a subgroup. How do you prove that a particular subset is a subgroup? Well, how do you prove anything is a group? Right? You have the four. You go through the 4 tests. Closure, it's got to be closed, it's got to be associative, there has to be an inverse. Remember, there's only one. Proved that in the previous lecture, one of In fact, the very first theorem we did in talking about groups. So there's a unique inverse, just one, and the fourth property, for every element there's an inverse element. Okay. Now, so to prove that something's a subgroup, you just prove that it's a group using the same binary operator as your parent group, your G. But look, I've put here only 3 of those 4. Now what's missing? So you've got here closed, the unit, and the inverses. So one of those 4 is missing. Which one? Well, associativity. Now why is that? Well, actually proving associativity for a group often is a real pain, right? Because you have to test. Well, unless you can find some smarter argument, if you're forced to go through all the combinatorics, I mean, it can be a real pain. Because think about how many cases you have to test. Like if the order of G, this bar, sort of like the magnitude, the size of. So if the order, in other words, how many elements, if the order of G is n, then how many ways can you do this? Test this. Right? Well, there's n elements you could put here, and here's n.